Module 1, Lecture B, Series Fundamentals. By the end of this lecture, you will be able to create Pandas series from Python objects and external data using idiomatic Pandas 2.3.1 syntax. Use positional and label-based indexing on series to select, slice, and filter data safely. Handle series dtypes and missing values using appropriate Pandas 2.3.1 methods. Building series objects. Series from lists and dicts. For simple one-dimensional data, you might start with a basic Python list, such as daily temperatures or sales numbers. A Pandas series builds on this by pairing each value with an index, usually starting at 0, similar to a list, but with more flexible labels. This indexed structure makes it easier to align your data with other datasets and integrate it into larger analyses. In effect, a series wraps your raw data so it is ready for more advanced operations like aggregation and joining. In Pandas, when you create a series from a dictionary, the dictionary keys automatically become the index labels and the values become the data. This preserves the original meaning of each entry without requiring you to set the index manually. The resulting series behaves like an ordered map, so you can access values by their labels and rely on those labels for operations such as alignment and joining. This makes it easy to integrate labeled data into Pandas. Analytical tools. Choose between creating a series from a list or from a dictionary based on how your data is structured. If the data is ordered but has no meaningful labels, such as a sequence of sensor readings, a list is a simple starting point and you can set the index later. If the data already has useful labels, like product codes, a dictionary is better because it preserves those labels and lets you access values by name right away. In either case, the series becomes a foundation for more advanced tasks such as grouping and joining, helping you manage data from many sources as your analysis grows more complex. Python code, series from lists and dicts. Using the Pandas library, you can create a series from both Python lists and dictionaries. When you build a series from a list, Pandas automatically assigns a default integer index starting at 0, so each value is labeled with a simple position number. In contrast, when you create a series from a dictionary, the dictionary keys become the labels or index for the series. This shows how Pandas uses list positions or dictionary keys to define how data is indexed in a series. We begin by importing the Pandas library because it provides the series data structure we need. A series is a one-dimensional labeled array that lets us store and work with data in an organized way. By bringing in Pandas, we gain powerful tools for creating, accessing, and manipulating this kind of structured data efficiently. We begin by creating a list of daily high temperatures in Fahrenheit, containing 4 integer values, 68, 70, 72, and 71. These numbers represent the recorded high temperatures over 4 days. This list will then be used to build a Pandas series so we can handle the temperature data in a more structured way and take advantage of Pandas data manipulation features. Using Pandas, we can create a series from a list of Fahrenheit temperatures, and Pandas will automatically assign integer indexes to each value. These indexes start at 0 and increase by 1 for each temperature in the list. The resulting series stores each temperature together with its index. which makes it easy to access and manipulate the data. We display the series created from the list so we can see the values together with the integer indexes that Pandas assigns automatically. This lets us confirm how Pandas generates default index labels when a series is built directly from a list. Observing this output helps us understand the basic indexing behavior of a Pandas series. We begin by building a dictionary that links each city name to its current temperature in Fahrenheit. Cities such as New York, Chicago, and Dallas serve as the keys, and their temperatures are the values. This structure makes it easy to convert the dictionary into a Pandas series, where the city names automatically become index labels. As a result, we can quickly look up temperature data by referring directly to each city. When we create a Pandas series from a dictionary, the dictionary's keys, such as city names, automatically become the index labels. This means each city name directly labels its corresponding value in the series. As a result, we can quickly look up temperature data by using the city name, and the data is stored in a clear, well-labeled structure. When we print the series created from the dictionary, it displays the city names as index labels and their corresponding temperature values. This output lets us clearly see how each city is paired with its temperature. In other words, the printed series provides a labeled view of the data, showing both the indexes and their associated values in a simple, readable form. This script shows how Pandas creates series objects from different data sources and how that affects their indexes. First, it builds a series from a list of Fahrenheit temperatures, where Pandas automatically assigns integer indexes starting at 0. Then it creates a series from a dictionary that maps city names to temperatures, so the city names become the index labels. By comparing the two outputs, you can see the difference between default integer indexing and labeled indexing based on dictionary keys. Custom series indexes. In Pandas, one-dimensional labeled arrays let you replace default integer positions with custom index labels, which makes your data more meaningful. By assigning descriptive labels, such as month names for sales or respondent IDs for surveys, you improve readability and clarity. This labeling helps you better understand your data and integrate it more effectively into further analysis tasks. When you create labeled arrays from a list or sequence in Pandas, you can supply a separate set of index labels that matches the length of the data. Each value is then paired with its label, which makes it easier to understand and work with the data. This is especially useful when your data has natural keys, such as product codes or building names. For instance, you can label energy consumption values by building names like library or gym instead of using numeric positions. Using meaningful labels simplifies selecting and inspecting data and helps reduce errors compared to relying on numeric indexes alone. Custom indexes are important when creating labeled arrays from dictionaries or working with multiple datasets. The dictionary keys become the index labels, so using clear, descriptive keys improves readability. When arrays share the same custom index, such as region codes, Pandas aligns data by these labels instead of by position. This label-based alignment lets you safely combine and transform datasets, even if their order or labels differ. Designing thoughtful custom indexes is therefore essential for effective data handling. Python code. Custom series indexes. This section explains how to create a data series with custom index labels to make the data easier to understand. It contrasts the default integer index, where positions are numbered automatically, with a custom index that uses meaningful text labels. By assigning clear labels, you can more easily identify and select specific values in the series. Overall, custom text indexes improve clarity and make working with the data more intuitive than relying only on default integer positions. We begin by importing the Pandas library so we can use its series data structure. A series lets us create and work with one-dimensional arrays that have both default and custom indexes. By bringing in Pandas, we gain powerful tools for handling labeled data efficiently and performing common data manipulation tasks. We begin by creating a list of 4 numbers that represent sales figures for 4 consecutive months. This simple collection of values will later be turned into a Pandas series. Using the series will let us see how such data can be indexed and accessed efficiently. The key idea is that the original list provides the raw monthly sales data that the series will organize and manage. We create a Pandas series from a list of sales values using the default integer index, which starts at 0 and increases by 1 for each entry. This automatic indexing lets us refer to each sales value by its position in the series. After creating it, we print the series so we can see each sales value paired with its corresponding default index. We create a custom index for a Pandas series by using month names instead of default numeric positions. First, we define a list of month labels from January through April. Then we build the series with the sales values and assign these month names as the index. This links each sales value to a specific month, so we can refer to data by month name rather than by position. Finally, we display the series to show the sales values alongside their month labels. We begin by printing a short message to explain that we are selecting the sales data for February using a label-based index. Then, we retrieve the February sales value from the custom series by referring to the label Feb. This shows how descriptive labels make it easy and intuitive to access specific entries in the series. Overall, the example highlights that label-based indexing improves clarity when working with particular data points. This example shows how a Pandas series can use both default and custom index labels. It first creates a series with the usual integer index to store sales values for 4 months. Then it builds another series that uses month names as labels, which makes it easier to refer to specific months. Using this labeled series, it retrieves the sales value for February, demonstrating how label-based indexing can make data access more intuitive. Naming, series, and types. Once you understand basic one-dimensional data structures, the next step is to give them clear names and recognize their data types. Meaningful names, such as daily revenue or exam scores, make your arrays easier to interpret and share. This becomes especially important when you work with several arrays at once, like comparing predicted and actual values. Clear naming and awareness of data types help you organize related measurements and carry out more effective analysis. When working with data structures, you should pay close attention to the data types they contain, because these types determine which operations are valid and efficient. Many libraries provide specialized types beyond basic numbers and text, such as types for dates, times, and categories. Although the library will guess the type when you create a labeled array, its guess may not match your intent. For example, treating product codes as numbers instead of text. Being deliberate about data types helps you avoid mistakes like averaging identifiers or sorting timestamps incorrectly. When working with data, clear naming and correct data types are essential for accurate analysis. Descriptive names, such as particulate matter in micrograms per cubic meter, make it obvious what each value represents. Choosing appropriate types, like floating point numbers for fractional measurements and date-time types for timestamps, helps ensure proper handling of the data. In other domains, such as customer churn analysis, using a boolean type for a churn flag and a categorical type for subscription tier turns raw data into structured, self-explanatory information that is easier to analyze and interpret. Python code, naming series and types. In this section, you will learn how to give series objects clear names and check what data types they contain. You will see how the library automatically infers data types when you create a series in different ways, and how this affects how the data is stored and used. Finally, you will practice changing the data type of a series when the automatically inferred type is not what you want, so you can ensure the series matches your analysis needs. We begin by importing the Pandas library so we can work with its data structures, such as series and data frames. This step enables us to use Pandas tools for organizing, manipulating, and analyzing data. Once imported, Pandas becomes the foundation for handling data throughout the script. We begin with a list of daily sales values in dollars and use it to create a Pandas series, which is a one-dimensional data structure. We then give this series a descriptive name, daily revenue in US dollars, so its purpose is clear when we work with it later. Finally, we display the series, which shows both the revenue values and the assigned name for easy identification. We start by printing a short message to indicate that we are about to check the data type of the revenue series. Then we look at its data type attribute, which tells us what kind of values the series contains. In this example, it shows that the values are stored as floating point numbers. This confirms that the revenue is treated as decimal numbers, which is important for performing accurate financial calculations. We begin by creating a list of product codes, which are numeric values used as identifiers rather than for calculations. From this list, we build a Pandas series and give it a clear, descriptive name to show that it represents product code identifiers. This naming step helps keep the data's purpose obvious when we work with it later. Finally, we display the series to check its contents and structure before making any further changes, such as adjusting data types. Before converting the product code series, we first check and display its inferred data type. This shows how Pandas has automatically interpreted the values from the original input. By examining this data type, we can see whether the series is treated as numeric or something else. This information is essential for deciding if we need to perform a type conversion. We convert the product code series to a string data type using the Pandas type method so that these values are treated as identifiers rather than numbers. This prevents accidental numeric operations, such as addition or averaging, that would not make sense for codes. After converting, we print the series to confirm that the values are now stored as strings. This verification step ensures the data type matches the intended use of the product codes. The code checks that the product code's data has been successfully converted to a string type by printing its data type. It also prints the name of the data series to confirm that this descriptive label is still intact. Keeping both the correct type and a clear name helps maintain clarity when working with the data. This script shows how to create and manage Pandas series with attention to names and data types. It first builds a series for daily sales revenue, gives it a descriptive name, and confirms that its values are stored as floating point numbers. It then creates a series of product codes, which are numeric identifiers that Pandas initially treats as integers. To avoid accidental numeric calculations on these codes, the script converts them to strings while keeping the same descriptive series name. The final result confirms that the data type has changed to string, demonstrating how to control and adjust data types in Pandas. Series Indexing Essentials. Label-based selection. Label-based selection means accessing data by its meaningful labels instead of by numeric positions. This is especially useful for labeled datasets, such as stock prices indexed by date, where the label carries important information. You can use labels to retrieve single values, multiple values, or ranges between two labels. Because it relies on the semantic identity of labels rather than their order, this approach makes code clearer and more stable as the data changes or grows. Label-based selection uses the exact labels in your index, including their type and order, to choose data. For date-based indices, you can select specific days or a range of dates and capture everything within that interval. For string-based indices, such as product codes, selecting by exact strings keeps the original labels unchanged, which is helpful in tasks like time series analysis or customer analytics. This approach stays reliable, even if the physical order of the data changes, as long as the labels themselves remain consistent. When selecting data by label, it is important to understand how labels behave, especially when they are not unique or look like integers. If your index contains duplicate labels, a label-based selection will return all rows with that label, which can be useful but may surprise you if you expect only one match. You should be clear about whether you are selecting by label or by position, particularly when labels are integers. To reduce confusion and errors, design your index with meaningful, unique labels so your code matches how you naturally think about the entities in your data. Python code, label-based selection. In this lesson, you will see how to use basic label-based selection with a simple Pandas series. We will compare selecting a single label, selecting multiple labels at once, and using label ranges to slice the data. The focus is on how these different forms of selection work and how they affect what values you retrieve. You will also see that labels remain consistent and reliable, even if the order of the data in the series changes. We begin by importing the Pandas library so we can work with its data structures, such as series and data frames. This step is necessary because it gives us access to Pandas tools for organizing, analyzing, and manipulating data. Once imported, Pandas can be used throughout the script to handle data efficiently and flexibly. We create a Pandas series to store daily temperatures in Fahrenheit using 4 values: 68, 70, 72, and 71. Each temperature is linked to a specific day of the week, with Monday, Tuesday, Wednesday, and Thursday serving as index labels. This structure lets us look up a temperature by naming the day, making it a simple and intuitive way to work with time-based temperature data. We start by looking at the entire series of daily temperatures, measured in degrees Fahrenheit. Each temperature value is linked to a specific day of the week, which serves as the index label. Seeing this full output makes it easier to understand how the data is organized and how each day's label corresponds to its temperature. To find the temperature recorded on Wednesday in a Pandas series, you use the loc accessor with the label WED. This method accesses data by its label rather than by a numeric position. It is especially helpful because it lets you work with clear, human-readable labels instead of index numbers while retrieving the corresponding value from the series. We begin by indicating that we are selecting temperatures for specific days, then use the loc feature of a Pandas series to access the values for Monday and Thursday. By giving loc a list of the day labels, such as mon and thu, it returns the corresponding temperature values from the series. This shows how to select multiple entries based on their labels instead of their positions, which is useful when you want to retrieve particular data points directly by name. We start by printing a message to explain that we are selecting temperatures from Monday through Wednesday, which sets the context for the operation. Then, we use the label-based selection feature of a Pandas series, called the loc method, to take a slice from the label mon to the label wed. This returns the temperatures for those specific days. The key idea is that label-based slicing lets us select a continuous range of data using the labels themselves instead of numerical positions. We reorder the temperature data by using the sort values feature in Pandas and choosing descending order, which arranges the temperatures from warmest to coolest. The sorted data is saved as a new object and then printed so we can see the values in this new order. This example shows that even if the order of the data changes, we can still reliably select values by their labels, because label-based selection does not depend on the position of the data. This script shows how to use label-based selection with a Pandas series of daily temperatures. It first creates a series with weekday names as labels, then selects a single value, such as the temperature for Wednesday, using its label. It also demonstrates selecting multiple days at once by passing a list of labels, and selecting a continuous range of days, such as Monday through Wednesday. Finally, it reorders the series from warmest to coolest to show that label-based indexing still returns the correct values, even when the data is rearranged. Overall, it highlights that label-based selection in Pandas is both stable and flexible. Positional indexing with iloc. Using the iloc accessor lets you work with a series by the position of its elements rather than their labels. This matters because labels are not always simple numbers and can be things like month names or timestamps. If you assume labels behave like positions, your code can break or give wrong results. By using iloc, you clearly state that you are working with positions, such as the first or last element, which makes your code easier to understand, reuse, and maintain, even if the index changes. Think of using the iloc indexer as working with a simple list where positions start at 0 for the first item, 1 for the second, and so on. You select data based on these positions, either choosing a single item or slicing out a range to create a smaller series. For instance, you might take the first 7 days or the last 5 days of a month's temperature readings, focusing only on their order. The slicing rules match standard Python behavior by including the starting position and excluding the ending one, which helps prevent off-by-1 mistakes. Using position-based indexing with the iloc tool lets you work with data by its order instead of its labels, which is especially useful when labels may change. It supports tasks like selecting every nth element or aligning series by their positions. In practice, this can mean choosing the last set of trading days in finance or the first group of exam scores in education. Focusing on order rather than labels makes code clearer, reduces errors, and encourages a deliberate choice between label-based and position-based access depending on what your analysis requires. Python code. Positional indexing with iloc. This lesson focuses on using positional indexing with the iloc feature on simple Pandas series. It explains that iloc always uses zero-based positions, meaning it selects data by where it sits in the series, not by its label. Clear printed examples show how a value with an integer label can differ from the value at the same integer position. By comparing label-based access with position-based access, you learn to avoid confusing integer labels with zero-based positional indexing. We begin by importing the Pandas library so we can work with its data structures in Python. This step gives us access to tools for handling series and data frames. With Pandas available, the script can perform powerful and flexible data manipulation. Importing Pandas is therefore an essential first step before working with tabular data in the code. We create a Pandas series to represent monthly sales in dollars using 4 values, 1200, 1500, 900, and 1600. Each value is assigned a custom integer label of 10, 20, 30, or 40, which are not consecutive. This example is used to show that positional indexing in Pandas depends on the order of the data, not on these custom labels. Understanding this distinction helps avoid confusion between accessing data by label and accessing it by position. We begin by showing the full sales series so we can see both the custom integer labels and their associated values. This makes the structure of the data clear, especially when the labels are not consecutive numbers. Viewing the series in this way is important because it prepares us to distinguish between accessing data by its labels and accessing it by its position in the sequence later in the code. In Pandas, the iloc method lets you access elements in a series by their position instead of by their label. For example, you can get the first element by using position 0, since iloc uses zero-based indexing. This is especially helpful when the labels are not simple consecutive integers or do not start at 0. After retrieving the element, You can print it to see the value stored at that position and confirm how iloc works. In this example, we use the iloc method from Pandas to select the first two elements of a series based on their positions. Because iloc uses zero-based indexing, we specify a range that starts at position 0 and stops before position 2. This captures the elements at positions 0 and 1, which are the first and second items in the series. The output then shows these two elements selected by their positions rather than by their labels. We use the iloc method with a negative index to get the last value in the sales series based on its position. A -1 index always points to the final element, no matter how long the series is. This lets us reliably retrieve the last entry without knowing the series length in advance. We then print this value and note that it was obtained using iloc with a negative index. In this example, we use the loc method from Pandas to access a value in the sales series by its label rather than by its position. We specifically look up the entry whose label is the word 20. This illustrates label-based selection, which is different from positional indexing that uses numeric positions. After retrieving the value, we print it to show the element that corresponds to the label 20 in the series. This script shows how positional indexing works in Pandas when a series has non-consecutive integer labels. It first prints the full series so you can see the custom labels and their sales values, then uses the iloc indexer to access data by position instead of by label. It demonstrates getting the first element, slicing the first two elements using a half-open interval, and using a negative index to reach the last element. Finally, it compares this with the loc indexer by retrieving the value whose label is 20, emphasizing the difference between label-based and position-based indexing, and showing that iloc ignores the actual labels. Boolean series filtering. Boolean series filtering in Pandas uses true and false values to decide which elements of a series to keep. Instead of selecting by position or label, you apply a condition, such as checking whether values exceed a threshold or match a category. Pandas evaluates this condition for each element and creates a new series of Boolean values that serves as a mask. You then use this mask to index the original data, returning only the entries marked as true while preserving their original index labels. Combining multiple conditions in Boolean series filtering lets you ask more specific questions about your data, such as finding days that are both hot and have complete measurements, or products that match both a price range and a category. You create separate Boolean series for each condition, and then combine them using logical operations like and, or, and not. This approach produces complex but readable filters. Because Pandas aligns these Boolean masks by label, it filters accurately even when you use related series, making this method safer and more expressive than relying on numeric positions. When using Boolean series filtering, you must handle missing values and data types carefully to avoid incorrect results. Clean the data first by filling in or dropping missing entries and converting text to suitable numeric or date and time types. This preparation ensures that your filter conditions behave as intended. In real applications, such as financial analysis or selecting patient groups, well-constructed conditions and proper handling of missing values let you accurately extract the exact subset of data you need. Python code, Boolean series filtering. This section explains how to use basic Boolean filtering on a simple set of temperature values. You learn how to create conditions that produce true or false values for each entry, forming a Boolean mask. That mask is then used to select only the temperatures that meet the condition. The process also shows how to combine multiple conditions safely while keeping the original index labels intact. We begin by importing the Pandas library, which is a key tool in Python for working with data. Pandas offers data structures such as series and data frames that make it easier to organize and manipulate information. In this script, we use Pandas to create and manage a series of temperature values, and then apply operations like filtering based on specific conditions. We create a Pandas series to store daily high temperatures in Fahrenheit, using the values 68, 72, 90, 95, 60, and 85. We give this series the name HighTempF. With this setup, we can conveniently work with and analyze the temperature data using Pandas tools. We begin by looking at the original series of temperatures, which is automatically given an integer index starting at 0. Each temperature value is paired with one of these index numbers, creating a clear mapping between positions and values. By printing the series, we can see both the temperatures and their index labels together. This gives us a clear understanding of how the data is organized before we apply any filtering. We create a Boolean mask to find days when the temperature is above 80 degrees Fahrenheit by comparing each value in the temperature series to 80. This comparison produces a series of true or false values, where true marks a day hotter than 80. We then print this mask to quickly see which days meet the temperature condition. We use a Boolean mask to filter the series so that it keeps only the temperatures from days hotter than 80 degrees. By indexing the series with this mask, we get a new series that contains only the values where the condition is true. We then print a short message to explain that these are the temperatures on hot days and display the filtered series showing only those values. We create a Boolean mask to mark all days when the temperature is below 90 degrees Fahrenheit. This mask labels cooler days as true and all other days as false. We then use it to filter the data, so we only keep and analyze the cooler temperature values that meet this condition. We combine two Boolean masks using a logical AND operation to find days when both conditions are true. Temperatures are higher than 80 degrees and lower than 90 degrees Fahrenheit. This produces a new mask that we apply to the original temperature data. The filtering step keeps only the temperatures that satisfy both limits, so we end up with a subset representing moderately hot days. Finally, we display these selected temperatures, showing only the values that meet the combined criteria. This script shows how to use Boolean masks in Pandas to filter data. It starts with a series of daily high temperatures in Fahrenheit and creates a mask that marks which days are hotter than 80 degrees, then uses that mask to display only those hot days. It then builds another mask for days cooler than 90 degrees. By combining the two masks with logical AND, it selects moderately hot days between 80 and 90 degrees. The example illustrates how Boolean logic can be applied to pick out specific data points while keeping their original index labels. Series, dtypes, and missing. Inspecting series, dtypes. When working with a one-dimensional labeled array in Pandas, it is important to know the data type of its values because this controls how the data is stored, how fast operations run, and which operations are valid. For example, daily temperatures might use a floating point type, while product identifiers might be stored as text. By checking the data type, you can confirm that the data matches your expectations. If you expect numbers but see text instead, it likely indicates a problem in how the data was loaded or cleaned and can cause numeric operations to fail or give incorrect results. When working with mixed or ambiguous data, such as survey answers or sensor readings, it is important to check the data type. A column may look numeric, but actually contain numbers, missing values, and markers like NA, which can cause the library to assign a generic, less efficient type. By inspecting the type, you can decide whether to clean the data, convert it to a more specific numeric or categorical type, or leave it flexible. This helps prevent bugs, like accidentally comparing strings to numbers or misusing category information. Understanding data types is essential for handling missing values correctly, because each type treats missingness differently. Floating point numbers can directly represent missing values, while integers often need a more flexible or nullable type. And newer nullable versions of integers, booleans, and strings behave differently from traditional types in some operations. By checking the data type before you change missing values, you can better predict what will happen, choose appropriate methods, and avoid unexpected type conversions or data loss. This awareness is especially important for reliable analysis when cleaning clinical data or processing survey results. Python code, inspecting series dtypes. We will look at simple, beginner-friendly ways to inspect the data types of a series and see how they are reported. You will observe how mixing different kinds of values, such as numbers and text, can cause the library to automatically change the inferred data type. We will also connect these data types to how missing values are handled and explain why understanding them is important for later data cleaning steps. The script starts by importing the Pandas library, which is necessary for working with data structures such as series and data frames. This import gives us access to Pandas tools for data manipulation and analysis. Throughout the code, these tools are used to manage data and examine the data types stored in series. In short, importing Pandas is the first step that enables all the later operations in the script. We create a numeric series in Pandas to store daily high temperatures in Fahrenheit, using a list of floating point numbers for each reading. Using floating point values ensures the data is treated as numeric, so we can perform mathematical operations and statistical analysis on it. This consistent numeric data type is important for any later processing or analysis steps we want to apply to the temperature data. We start by printing a message to indicate that we are about to show the temperature series. Then, we display the series itself, which holds daily high temperatures in degrees Fahrenheit. After that, we print the data type of the series to see how these numeric values are stored. Checking the data type helps confirm that the series is treated as numeric data, which is important for performing correct calculations and data manipulations later on. We create a Pandas series that contains both numeric values and non-numeric entries, including a text marker and a missing value. Because of this mix, Pandas assigns the series the object data type, which is flexible enough to hold different kinds of data in one place. This example shows how Pandas treats mixed data within a single series and prepares us to explore data cleaning steps later. We begin by displaying a series that mixes numeric values with non-numeric entries, such as a text string and a missing value. When we check its data type, we see that Pandas has set it to the object type. This happens because the series contains different kinds of data, and the object type can hold that mixture. This automatic promotion to an object type is important, since it influences how we will handle and process the data later on. We use the Pandas convert to numeric function to turn the mixed reading series into a numeric type. This function tries to convert each value into a number, and when it encounters something that cannot be converted, such as a non-numeric string or a missing value, it replaces it with a special value called nan, meaning not a number. Doing this ensures all entries share a consistent numeric format, which is essential for performing numerical operations and data analysis on the series. We first display the converted series to confirm that it now contains only numeric values instead of the original mixed data. Then we check and print its data type to show that it has been updated to a numeric type. During this conversion, any missing or non-numeric entries are turned into nan values. This process prepares the series for reliable numeric operations and further analysis. This script shows how Pandas manages data types in a series. It first creates a series of Fahrenheit temperatures, which Pandas stores as floating point numbers and reports with a numeric data type. Then, it builds a series with mixed content, including a string and a missing value. So Pandas switches the data type to a general object type. Finally, the script converts this mixed series to a numeric type, turning non-numeric entries into missing values. The end result is a float series with non-numeric data replaced by non, which is important for performing numerical operations. Finding missing values. When working with a series, you must check for missing values because they can distort your analysis. These gaps are stored as special placeholders that mean the value is unknown. For example, in a series of daily air quality, missing entries might come from sensor problems. Before you calculate results or combine this series with other data, first identify any missing values so you can decide how to handle them appropriately. To find missing entries in a series, you can use methods that return a new series of true or false values indicating where data is missing. This Boolean mask has the same index as the original data, so it lines up perfectly with each entry. For example, if some customers do not enter their age in an online form, those positions will be marked as true, while valid ages are marked as false. You can then count missing values, focus on particular problems, or combine this mask with other conditions, creating a clear and reproducible way to handle incomplete data without guesswork. Identifying missing values is essential for judging how complete and reliable your data is. You can start by creating a mask that marks which entries are missing. Then summarize it to count them or group them by categories such as product lines or regions. This helps you detect patterns like missing data concentrated in certain months, which may signal issues such as reporting delays. Noticing these patterns early guides you on whether simple fixes are enough or deeper investigation is needed. And treating this step as fundamental helps keep your analysis robust and trustworthy. Python code, finding missing values. In this example, you work with a simple Pandas series to detect missing values. You create a boolean mask that marks each position as true if it is missing and false otherwise, which clearly shows where the gaps are. You then count how many entries are missing to get an overall summary. Finally, you use the mask to filter the series so you can inspect only the missing entries in more detail. We begin by using the Pandas library in Python, which is a key tool for working with data. Pandas offers powerful data structures, such as series and DataFrames, that make it easier to organize, manipulate, and analyze datasets. These structures are widely used in data analysis tasks and form the foundation for many data workflows in Python. We begin by creating a Pandas series to store daily temperatures measured in degrees Fahrenheit. Some entries in this series are missing and are represented by special missing value markers, such as none and nan. The series is given a name that indicates it holds temperature data in Fahrenheit. This setup reflects real-world datasets, where some temperature readings may be unavailable, and prepares us to work with and analyze data that includes missing values. We start by printing the original series of temperature values, which contains both valid readings and missing entries. Seeing the full series helps us visually confirm where data is present and where it is absent. This simple step gives us a clear overview of how complete the temperature dataset is before we perform any further analysis. We apply the isna method to the temperatures series to create a mask that marks missing values as true. This mask clearly shows which entries are missing. Identifying these gaps is essential because it lets us focus on and properly handle or analyze the missing data in the series. We now display a Boolean mask that shows which positions in the series contain missing values. In this mask, entries marked as true indicate that the corresponding value in the series is missing. This makes it easy to visually locate and understand where data is absent in the series. The code uses a Boolean mask to find missing values in the series, where each missing entry is marked as true. It then applies the sum operation to this mask. Because true values are counted as 1, the sum gives the total number of missing data points. This provides a quick way to count all missing values in the series. We create a short summary that reports how many temperature readings are missing. To do this, we convert the stored count of missing values into a whole number so the result is clear and easy to interpret. We then display this number, giving a quick overview of the amount of missing data in the temperature series. We use the Boolean mask to filter the series so that only entries marked as true, which represent missing values, are selected. This lets us view just the missing temperature readings together with their original indices. By isolating these entries, we can more easily inspect and address the data points that require attention or correction. This script shows how to find and handle missing values in a Pandas series of daily temperatures. It first prints the original data, which includes both valid temperatures and missing entries marked as none or not a number. It then uses a method that returns a series of true or false values to indicate which positions are missing and prints this mask. By summing the true values, the script counts how many data points are missing and displays that number. Finally, it uses the mask to print only the missing entries with their original positions, which helps you see exactly where data is absent, an important step in data cleaning and preparation. Filling and dropping nans. When you encounter missing values in a one-dimensional data set, you must decide whether to fill them, drop them, or leave them as they are, based on the context and your analysis goals. For example, filling gaps in daily temperature data with nearby averages can be reasonable because temperatures change gradually. While in financial data, creating values may be misleading, so removing those entries can be safer. Always consider what the data represent, how much is missing, and its context, and how sensitive your results are to these choices before deciding on a strategy. When dealing with missing values, a process called imputation, you can fill gaps in several ways. Simple options include using a constant like 0, a label such as unknown, or a default value like a national average. You can also replace missing entries with summary statistics, such as the mean or median. For time-ordered data, it is common to carry the last known value forward or the next known value backward. More advanced methods use model-based predictions, but these are still estimates and should be interpreted cautiously in your analysis. Dropping missing values is useful when there are only a few gaps or when the absence of data itself is informative, because it simplifies analysis and avoids errors from poor imputation. However, removing records can also discard important information and change how the data represents the population, such as when high-income survey responses or incomplete medical records are disproportionately excluded. A common compromise is to drop entries that lack critical variables while filling in less important gaps. Whatever approach you choose, it is essential to document how missing values were handled so you can understand their impact on your results. Python code, filling, and dropping nans. This lesson shows how to handle missing values in a Pandas series using simple built-in methods. You will see how to fill in missing entries when that is appropriate, and how to safely drop missing values when it makes more sense to remove them. The focus is on understanding how each choice affects the resulting series and how it changes the summaries you print or compute from your data. In this lesson, we use the Pandas library in Python to handle and analyze data. Pandas offers key data structures such as the series and DataFrame that make data manipulation easier. Here, we focus on creating and managing a series of temperature readings. This example will help us demonstrate how to work with and handle missing data in a practical way. We begin by creating a Pandas series to store temperature readings in Fahrenheit, including some missing entries. These missing values are written as none in the data, and Pandas automatically converts them to special missing value markers called nan. This simple setup gives us a data set with gaps, which we can then use to demonstrate practical techniques for detecting and handling missing data in analysis. We begin by printing the original temperature series so we can clearly see which values are missing. This display reveals where the data contains gaps, often shown as not a number entries. Visually confirming these missing points helps us understand the state of the dataset and prepares us for later steps, such as cleaning the data or filling in those gaps. To handle missing values in our temperature series, we replace them using a simple imputation method. We apply the Pandas fill missing values function and use the mean of the observed temperatures as the replacement. This means each missing entry is estimated by the average of the available data. After filling in these values, we print the updated series to confirm that all missing temperatures have been successfully replaced with the mean. We handle missing values in the temperature data using the forward fill method. This means each missing value is replaced with the most recent available temperature, which works well when temperatures are expected to change gradually. After applying forward fill, we review the updated series to see how the gaps have been filled with the last known readings. We begin by applying the drop missing values method to the temperature series, which removes any entries that contain missing data. This step filters the series so that it includes only complete temperature observations. Working with this clean series helps us analyze or process the data without complications from missing values. After cleaning, we display the updated series to show only the valid temperature readings that remain. This script shows how to handle missing temperature readings stored in a Pandas series. It first displays the data with gaps, then fills those gaps using 3 common strategies. One approach replaces missing values with the mean of the available temperatures, providing a simple imputation. Another uses forward filling, carrying the last known reading forward to fill later missing entries, which suits gradually changing data. The final approach removes all entries with missing values, keeping only complete observations. Comparing these results highlights how each method changes the completeness and integrity of the data. In this lecture, you learned to create Pandas series from Python objects and external data using idiomatic Pandas 2.3.1 syntax. Use positional and label-based indexing on series to select, slice, and filter data safely, and handle series dtypes and missing values using appropriate Pandas 2.3.1 methods. In the next lecture, Lecture C, we will go over DataFrame essentials. Thank you for your attention. See you all in the next lecture.